Good morning, Year 12s. Welcome to this incredibly important video on normal distribution. Normal distributions underpin a huge area of statistics, and it will relate to anything where there's a mean and the results are predictably distributed around the mean. For example, heights, weights, IQ scores, test scores, and a very simple graph here is birth weights. That would be about the mean. The vast majority of babies are within a set distance of the mean, and then very few are at the extremes, and this makes sense in terms of heights, weights. The vast majority of men is around 175 to 185 and 165. There are not many either side of that. Essentially, as you go away from the mean, there are fewer and fewer elements of the population. And this results in what we call a bell-shaped curve, and it comes up again and again in statistics. Now, this normal curve, or bell-shaped curve, has some properties that we should be aware of. Firstly, it is a distribution, so the integral under the area of it is 1. And even though in some distributions it wouldn't make sense to have negative values, so for example here, clearly the baby's birth weight's never going to be negative, that's why it's flat. Mathematically, it looks like this. Between negative infinity, all the way off here, and positive infinity, all the way off here, the area under must be 1. In reality, though, we don't have to go to positive or negative infinity to get that area. In reality, it's just a rounding error, or mathematically nice, that gives us that end area. This normal distribution can occur from summing other distributions, and this is something we'll look at in more detail later. But take for the example 1 dice, 2 dice, 3 dice, 4 dice. 1 dice, there are the probabilities, and they're evenly distributed, but it's not normal. So evenly distributed means there's a mean. In this case, the mean of 1 dice is 3.5, and it's evenly distributed either side, but that's not a normal curve yet. 2 dice, when we add them together, you double this mean, and we can see that 2 times 3.5 equals 7. That gets us there, and we get this more predictable drop off either side. And more dice, and we start getting this bell shape, which I'm terrible at drawing, and you're going to have to put up with some terrible drawing. Alright, note that we almost always assume normality, and in lots of questions you'll be working on the assumption that this is a normal distribution. Sometimes they'll ask what could be wrong with this assumption, and the answer will almost always be it might not be normally distributed. So for example, there are plenty of non-normal distributions. So take a rather odd one, which is cell boundary width. Very few cells have a very low cell boundary, and then it peaks up here, and then nothing beyond a certain point. Or this here is number of people and a greatness score. Clearly it's very arbitrary and a bit of a joke, but what this is saying is the vast majority of people here are not very great, and then very few are very great. Each of these data sets is what we call skewed. Skewed data involves long tails, and this is what we call negatively skewed, and this is what we call positively skewed. The way I remember that is if the tail, which is this side, is on the negative side, it's negatively skewed. If the tail is on the positive side, it's positively skewed. And that is terminology that is good to know and remember. And if you have a skewed data set, the mathematics we're about to do doesn't actually apply to it. Alright, so remember this function here. From negative infinity to positive infinity, f of x dx is 1. Well, that function, mathematically, is this, where rho there is standard deviation, and mu is mean. Now, don't freak out. You are, of course, expected to have this on your cheat sheet. I think it's even given in the data book. And if a graph is distributed using this, we say x is distributed, that's distributed, normally with a mean and standard deviation. Normally we write the standard deviation with a squared above it. So that actually, if you write it as a whole number, is just the variance. And be aware that if you see something distributed with, say, a mean of 10 and then it writes 4, what that actually means is that the standard deviation is 2. And that's a really mean trick. A nicer way to write it is it's distributed with a mean of 10 and a standard deviation of 2. or 2 squared there, meaning variance. Alright. Note probability distribution, say weight, let's go with, given that it's probably adult men, have a mean of 71. What this means is that the vast majority of people are bulked around that 71 point. Very, very few are over 100, and very, very few are less than 50. This looks different to cumulative distribution. Cumulative distribution, if we go to the 50 mark and go down, that there will be the 71.1. 71.7 rather. Alright, now I mentioned normal distribution is very predictable, in that we can predict the amount of data points gathered either side of a distribution. So for example, say the heights thing, if this is the mean height of 175, and I'm making these numbers up, and let's say the distribution had a standard deviation of 10. Now let's make it 5. 180, 170. What this is saying is that 68.26% of men lie within 1 standard deviation of the mean. And this applies to everything. So 62.26% of babies, weight, IQs, etc. lie within 1 standard deviation of the mean. 1 standard deviation up, 1 standard deviation down gives us 68% of the data set. If we add another standard deviation on, so in our case between 185 and 165, we get about 95% of the data set. So what that's saying is, in my made up numbers, 95% of men are between 165 and 185 centimeters. Now, again, I made the numbers up, might not be entirely accurate, but the idea is, if we go a couple of standard deviations out, we capture the vast majority of the data set. It's not evenly spread, where there's an equal chance of someone being 190 as opposed to 170. You're more likely to find a 170 centimeter person, 175 centimeter person than 190. Alright. Normal curvosaurus. I just thought it was a cute meme. Alright. Now, in terms of graphical significance, if we're thinking in terms of calculus, if we find the second derivative and set it equal to 0, it will equal 0 at these 2 points. 1 standard deviation out from the mean are non-stationary points of inflection. Alright, let's go into some practice questions. So, pulse rates of a group of 18-year-old students are normally distributed with a mean of 75 beats per minute and a standard deviation of 11 beats per minute. Anytime you're given a sentence question, I would be drawing a little sketch off to one side of a standard deviation, of a normal distribution, and then write in there. And this isn't going to be particularly pretty. Write in a mean of 75, and then look at where the normal distributions lie. So this is going to be plus 11, 86, take 11, 64. And then another one, 97, take another one, 53. Alright, then, now we've got an idea of where everyone's falling. The percentage of 18-year-old students with pulse rates of less than 75 beats per minute is closest to. Alright, well 75 was the mean, so less than 75 looks like that, which is half the data set, 50%. The percentage of 18-year-old students with pulse rates less than 53 beats per minute, here, or greater than 86, here. Now note, we will then have to go and refer to our normal curvosaurus up here. So this is 1 standard deviation down, 2 down, and this is 1 above. So from 1 above up, I'm just going to raise up here. From 1 above up is there. And 2 down is here. This adds to about 16%. And this adds to about 2.5%. So we're looking for about 18.5% here. There we are. anytime you get one of these questions, draw it out and visualize this as an incredibly important diagram in terms of the percentage of the distributions that fall there. And note they are cumulative. So everything right of this, you would add up 13.59, 2.15, 0.13, etc. Alright. Have a read of this. The weights of Jason's oranges are normally distributed. 84% of the crop weighs more than 150 grams, and 16% weighs more than 200 grams. Find the mean and standard deviation for the crop. Alright, first step, draw it out. I'm going to pause, you have a shot at it, and I'll draw out the answer in a sec. Alright, hopefully with your drawing you should come up with something looking like this. 16% weighs more than 200 grams. Well, remember 16% was, if you go one standard deviation up, everything to the right of that is 16% above it. 84% of the crop weighs more than 152 grams. So if you're thinking the other side, out here is 16% from that line, one standard deviation. Therefore, 84% must be the other side. So it's basically halfway in between these two. So that's 48, add 24 on. Take 24 off, we should get to this center value here. 24 is therefore the mean, and adding 24 onto 152, which is 176, is the mean. Sorry, 24 is the standard deviation, 176 is the mean. And therefore, what percentage of oranges weigh between 152 and 224? Well, here is 224. And what we're going to do is basically find the area of the curve from one standard deviation down to 2 above. One standard deviation down to 2 above. That middle bracket there is 68% plus another 13%. Remember the decimals. So we're looking at 68.26% plus 13.59. Add that together and you get 81 point something, and that will be your answer. Alright, note how all the questions so far have fallen exactly on standard deviation boundaries. And this leads us to be able to be very predictable in terms of the curve. But what happens when our point of interests don't fall exactly on the standard deviation? So here, if we have x distributed normally with a mean of 40 and a standard deviation of 10. Well, that there is 40. Standard deviation of 10 is 50, 30, 60, 20, etc. Find the probability that x exists between 37, so that's just here, and 48, there. Now, we can take an estimate of this probability. You can probably estimate that, well, if you knew that between here and there was 68%, it's a crude estimate, but you could say somewhere between 40 and 50% would make sense. However, we want to calculate this more accurately. Illustrate your answers means draw a normal curve. So we would rule this out nicely, draw a proper bell curve, and highlight in here that area there with the numbers written down the bottom of 37 to 48 is the area we're looking for. And it turns out our calculator can help us here. So if we bring up our calculator, exit, and if you go into statistics, so number 2, then go distributions, normal. And we want normal cumulative. Lower, upper. 37, 48. Standard deviation is 10. Not 110, just 10. And mean of 40. Execute, execute. And there is our probability of 40%. Or take that number times it by 100 is 40.6%. Nice. So we can get an estimate from what we know of the curve, and our calculator gives us the exact. Alright, here are two other ones. So this is a two-sided distribution, or probability distribution. This is one-sided. So what this is asking really is what's the probability that's over 45? So in our different color here, we're going to completely mess up the diagram. 45 is there, probably it's over 45 is all of that. Alright? So, what we do is we set our lower to 45 and our upper to 1e99. Now, in theory, we should be able to set them to infinity, but our calculator doesn't actually let us go to infinity. So if you type in 1 exp99, that is 1 times 10 to the power of 99. It's so close to infinity that the calculator won't know the difference. And then we hit execute, and we can see the probability that we fall in that region is 30.8%. And similarly again, less than 26, we can go in there, make the upper 26 lower. Do it quickly. Upper 26, lower negative 1 E99 is 8%. So the probability of being less than 26 is 8%. Alright. Honestly, I think I've had enough time doing this, so I'll skip that one, but there is one more I'd like to show you. We can combine, there we go, normal and binomial distributions, and these do come up. The time taken by students to complete the puzzle is normally distributed. A randomly selected student took 30 minutes to complete the puzzle. Calculate the probability the randomly selected student took 30 minutes to complete the puzzle. Alright, here we're asked for at least being the keyword, at least 30 minutes to complete the puzzle. So we're looking for the probability that x is greater than or equal to 30. And note that it's always equal to. You can't have strictly greater than. Which is why oh no, you can. Sorry, that was completely wrong. At least means strictly greater than 30. My bad. Alright, so we're looking at here, lower 30, upper effectively infinity, although it shouldn't take a student that long to complete the test. Standard deviation is 3.6 and mean is 28.3. Because it's about 1 standard deviation above, we should be thinking 31%-ish. Alright. Out of 10 randomly selected students, what's the probability that 5 or fewer of them took at least 30 minutes to complete the puzzle? So now, what we're thinking is students randomly selected either have a probability of success or failure. Here, success being they took at least 30 minutes, failure they didn't. Now there's two options, it's turned into a binomial distribution. So when students are randomly selected, we want the probability that it's binomial cumulative, which is an absolute mess. So here we have, back into our distribution, we go binomial cumulative. Here we don't want list, we want variable, where x is five, number of trials is 10, and the probability of success is that 0.318 that we calculated before. So the probability that 5 or fewer of them took at least 30 minutes to complete the puzzle is 93.8%. Alright, I think I've set a new record for my videos in terms of length. Thank you for getting to this stage. Enjoy practicing.